Let's take a look at two calculations for change in Gibbs free energy. First, we'll look at an isothermal expansion of a virial gas, and then we'll look at a constant pressure heating of an ideal gas. When I am expanding a gas at constant temperature, and I want to know how the Gibbs free energy changes when I do that, the question I'm asking in terms of mathematical symbols is how does the Gibbs free energy change when I change the pressure at constant temperature? I can easily get an expression for this derivative from my differential expression for the Gibbs free energy change, and I end up with this equal to the volume. If I were able to solve the virial equation for the volume, I could plug that equation in here, separate variables, and integrate. But I end up with a quadratic equation, and it's kind of messy to integrate that equation. And so I'm going to change variables and actually look at how the Gibbs free energy changes with the volume at constant temperature rather than the pressure. Remember that when we're doing an expansion or compression at constant temperature, we can think about it either as a volume or a pressure change, and we're free to choose which one we want to do. So in this case, it's going to be easier to look at it in terms of a volume change. So since I'm still at constant temperature, the first term in my differential expression is 0, and I only have to worry about differentiating the second term. And so what I need is an expression for the pressure, how the pressure changes with volume at constant temperature. And I can get that by differentiating my equation of state. And so if I take the derivative of pressure with respect to volume at constant temperature, I end up with minus RT over the molar volume squared minus 2 second virial coefficient divided by molar volume cubed. And that expression can then be plugged into my expression for how the Gibbs free energy changes with volume at constant temperature. So the Gibbs free energy changes with volume at constant temperature according to minus RT over molar volume plus 2B2 over molar volume squared. Now I just need to separate variables and integrate. And so dg is equal to minus RT dV divided by V. These are molar volumes. Minus 2B2 dV divided by molar volume squared. When I integrate both sides of this equation from the initial state to the final state, I get minus RT times the integral from the initial molar volume to the final molar volume, dV over V, minus 2 times the second virial coefficient, integral from initial molar volume to final molar volume, dV over V squared. And so delta G is equal to minus RT, natural log, of the molar volume final divided by the molar volume initial, plus 2B2, 1 over final molar volume minus 1 over initial molar volume. And there's my expression for the change in Gibbs free energy when I expand or compress a virial gas at constant temperature. Now let's look at how we would find an expression for constant pressure heating or cooling. So in this case, the pressure is constant, so this term is 0, and I'm going to change the temperature. So this is the term that I'm interested in. So the question I'm asking is, how does the Gibbs free energy change when I change the temperature, heat or cool, at constant pressure. And that expression is minus the entropy. So to solve this problem, we need an expression for the entropy, not the change in entropy, but the absolute entropy of the system. So this means that we need to understand how entropy changes with temperature at constant pressure. We know that this is equal to the constant pressure heat capacity divided by the temperature. So we could find an expression for the entropy if we separate variables and integrate this equation. So ds is equal to c sub p over t dt. And so if I integrate this expression from some initial entropy, and what we're going to do is we're going to use the standard state entropy at some temperature of interest. And typically those are tabulated at 298 Kelvin, so that would be a good temperature to start at, to any other entropy. And then I'm going to integrate from my beginning temperature, 298, to any other temperature. This gives me an expression which is S minus the standard state entropy at 298 is equal to, now if we assume the heat capacity is constant with temperature, that'll simplify things. So for a constant heat capacity, I can take that out of the integral, and then I have natural log of T divided by 298. And so my expression for the absolute entropy is the entropy at 298 plus a correction for not being at 298 Kelvin. So now I have an expression for the absolute entropy as a function of temperature. I can use this expression in my expression for how Gibbs free energy changes with temperature at constant pressure. And then I can again separate variables and integrate to get an expression for a change in Gibbs free energy when I heat or cool the ideal gas or my system at constant pressure. So let's plug that in. So we have dg dt at constant P is equal to the entropy, and I need a negative sign, at 298 minus the heat capacity times the natural log of any temperature divided by 298 Kelvin. And so then I just need to separate variables and integrate. So dg is equal to minus S at 298 plus the heat capacity times the natural log of T over 298 dt. Now I just need to integrate both sides, and so when I integrate dg from g initial to g final, I get delta g, and that's going to be equal to minus the entropy at 298, which is a set value, from T initial to T final dt, minus the heat capacity we've taken to be constant with temperature, the integral from T initial to T final of the natural log of T over 298 dt. The first integral is pretty easy to do because it's just the integral of dt, and so I end up with minus S at 298 times delta t. And then the second integral is a little trickier. If we look this up in a table of integrals, we can see that this is going to be equal to minus c sub p times t times the natural log of T over 298 minus T evaluated from T initial to T final. And so I end up with delta G is equal to C sub P minus S at 298, that quantity times delta T, I get this from this term, minus S at 298 delta T, and the term that results from taking C sub P times T evaluated from T final to T initial. These two minus signs cancel to give me a positive, and so I get C sub P times delta T. Then I also have the term that I get when I evaluate the natural log portion of the second integral. So I have T final, natural log of T final over 298, minus T initial, natural log of T initial over 298. And that is my expression for the change in Gibbs free energy when I heat or cool a gas at constant pressure. The important thing about these two examples is not that you memorize the final equations, but rather that you understand the process that we used to get those final equations. If you understand the process, then you can apply that to any problem, whether it be an ideal gas, a virial gas, a liquid, a solid, etc., and you will be able to come up with an equation for how to calculate changes in the thermodynamic variables.